Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. We will see a special instantiation of secret sharing, which we call as additive secret sharing, and we will see its security analysis. So, this additive secret sharing is also called as n minus 1 out of n secret sharing scheme. Namely, it is a special case of threshold secret sharing where t is equal to n minus 1. Namely, here you require to have a sharing mechanism in such a way that only when all the n shareholders make their shares available, then the secret can be reconstructed back. Okay. Namely, your X structure consists of just one subset, namely the entire subset of n parties, and hence your forbidden structure or unauthorized subsets will consist of n minus 1 or less number of parties. That means, we want a mechanism if any n minus 1 or less number of parties pool their shares, they should fail to learn the secret S. Namely, the probability distribution of their shares should be independent of the underlying secret, right. So, let us see the instantiation of this n minus 1 out of n secret sharing, and here we will perform all the operations, namely the sharing, reconstruction, all the operations we will perform over an abstract group G with an abstract plus operation. Okay. Remember, this is an abstract plus operation that need not be the numeric or the integer or a real number addition. Okay. And here the secrets and the shares will be elements of the group. That means, the dealer's secret will be an element of the group, the shares also will be element of the group, and so on. Okay. So, the main intuition behind the sharing algorithm is the following. The sharing algorithm basically divides the secret into n random shares, random looking shares, such that the sum of the shares, and by sum I need not mean in the integer sum sense, by sum I mean as per the group operation. The sum of the shares, the n random shares, should be equal to the secret S, but out of those n shares, if I focus on any n minus 1 shares, that should be independent of the secret S. That is a rough intuition behind this secret sharing scheme. So, now let us go directly to the sharing algorithm. So, I denote the sharing algorithm of this scheme as SH sub add. Add denotes the additive secret sharing. The input is the secret S, which is going to be an element of the group. So, remember, the sharing algorithm has to be randomized. Let us see where exactly the internal randomness is coming into picture. So, the first step of the algorithm will be the following. It will randomly pick n minus 1 shares, namely the first n minus 1 shares. Well, it could be the any n minus 1 shares, but just for the sake of simplicity and without loss of generality, assume that the sharing algorithm picks the first n minus 1 shares uniformly at random. From where? From the group itself. That means, remember I said the shares are going to be elements of the group. What I am saying is that pick the n minus 1 shares as random group elements. This notation belongs and then in subscript R denotes uniformly at random. Right. So, it could be the case that all S1 to Sn minus 1 are the same value, because you are picking S1 independently, S2 independently, Sn minus 1 independently. So, there is a non-zero probability that all of them are the same group element, or they could be all distinct, that is also a non-zero probability event, or it could be the case that all the odd indexed shares are the same or the even indexed shares are the same, and so on. So, all these events can occur with non-zero probability, because you are picking the first n minus 1 shares for the secret S uniformly at random from your underlying group. Now, we have to define or compute the value of the nth share. The nth share is computed as follows: you add the first n minus 1 shares, and by adding I mean as per the underlying group addition operation. You compute the additive inverse of S 1 plus S 2 plus S of n minus 1 and add it with your secret S, because again the interpretation of this minus operation is depending upon your underlying group. Here it means basically we are adding the additive inverse. So, let us denote the summation of first n minus 1 shares as x. S minus x basically means I am adding the additive inverse of x to the secret S, or in other words the way to interpret is that my Sn should be such that the summation of x and Sn should give me the secret S. Okay. That is the way the nth share is computed. Remember, all these actions are done as part of your sharing algorithm, and now the algorithm outputs the shares S 1 to Sn, and if dealer wants to share the secret S, it will run this sharing algorithm, compute S 1 to Sn, and the value of Si will be given to the party number Pi along with the private over the private channel between the dealer and the party number Pi. Okay. So, now you can see that why this algorithm is a randomized algorithm. Say for instance, if you execute this sharing algorithm with the same input S twice in succession, will you get the same values of S 1 to Sn? No, need not be, because the first time you run the sharing algorithm with input S, the shares S 1 to Sn minus 1 might be different. In fact, they are independent compared to the values of S 1 to S of n minus 1 when you run the sharing algorithm for the secret S in the second attempt, and that is why the sharing algorithm is randomized, right. So, again let us take the case of n equal to 4. If dealer wants to share the secret S as per the additive secret sharing in such a way that even if up to 3 parties combine their shares, they should fail to learn the secret, the dealer will do the following: it will compute the shares S 1, S 2, S 3, S 4 as per the secret S using this sharing algorithm, and respective shares it will communicate privately over the channel between the dealer and the ith party. Now, what will be the reconstruction algorithm? And for reconstruction algorithm, we need a mechanism where if all the n shareholders make their shares available, we should get back the secret S. So, the input for the reconstruction algorithm will be the vector of n shares S 1 to Sn, and it is very simple to get back the secret S. What you have to do? You just add the n shares S 1 to Sn, and because of the fact that your summation of S 1 to Sn is the secret S, you will get back the correct output. That is a very simple sharing algorithm and the reconstruction algorithm, right, done where the operations are performed over a group. So, correctness condition is trivial to verify, right, because you have only one authorized subset, namely the entire set of shareholders, and if the entire set of shareholders come together by running the rec algorithm, of course, they can construct back the value of your secret S. But what about the privacy condition? Does this scheme achieves the privacy condition? And for privacy condition, remember we have to formally argue that any subset of n minus 1 or less number of shareholders, their the probability distribution of their shares is independent of the value of the secret which dealer has shared. That is what we have to formally argue. And intuitively, before going into the proof, let me give you an intuition that why the privacy condition is true. We need all the n pieces to get back the secret. Even if one piece is missing, that one piece could have been any value from the group. and depending upon what value from the group would have been that missing piece implies a corresponding secret. That is why from the viewpoint of n minus 1 shareholders who are not supposed to get back the secret, it could be any value of the missing piece and hence as the share, as the missing share, and hence it could be any value from the group which dealer could have shared. So, I will make this intuition more specific by taking concrete examples of the groups. So, I will take two specific groups where I will show you the instantiation of this additive secret sharing, and for both these groups we will analyze the privacy property. So, let us take the first candidate group where my G, group G consists of all bit strings of length L bits, and my abstract plus operation is the bitwise XOR operation. So, I am sure all of you know what is the XOR operation. If you have 2 bits A and B, and if you perform their XOR, then the result will be 0 if A equal to B, otherwise it will be 1. In some sense you can imagine this XOR operation to be addition modulo 2. Now, what is this bitwise XOR operation? So, under the subscript you have this L. So, since my elements are now going to be L bit long binary strings, if I am given 2 long binary strings A and B consisting of L bits A0, A1 up to A of L minus 1, and in the same way B is B0, B1 up to B sub L minus 1, then A XOR B bitwise is basically the result of A0 XOR B0, that will be the first bit or LSB. In fact, you can that is the first bit, not the LSB. The next bit will be A1 XOR B1, the next bit will be A2 XOR B2 and so on. That is a definition of this bitwise XOR operation. And it is easy to see that this indeed is a group, because all your group properties are satisfied. You take the closure property, you take any L bit long string, perform the bitwise XOR operation, the result again will be an L bit long string. So, the closure property is satisfied, XOR satisfies the associative property, the binary string all 0 of length L bits, this is your additive identity element, and if you have X, then corresponding to where X is actually a bit string, then minus of X or X inverse is which is same as the string X itself, namely X inverse is X itself, because if you perform the XOR of X and X where both of them are L bit long string, you will get back the inverse additive identity element, namely the 0. Okay. So, it satisfies, in fact, this is an abelian group because the XOR operation even satisfies your commutative operation, commutative property, sorry, right. So, now imagine dealer has a secret which is some L bit long string, and if it wants to secret shares it, what it will do is it will first pick 3 random strings of length L bits uniformly at random, and they will be the first 3 shares, namely shares of P1, P2, P3, and the fourth share will be S minus the summation of the first 3 shares, and remember summation here is basically the XOR operation and subtraction here is also basically the XOR operation. So, the fourth share is such that the XOR of shares S1, S2, S3 and S4 gives you back together the secret S, and now the dealer will distribute the shares S1, S2, S3, S4 to the respective parties. So, now let us take a concrete value of L and see the real execution or one of the executions possible. So, imagine L is equal to 2 and the secret which dealer wants to share is the binary string 0 1, which only dealer knows. And remember, our goal here is to ensure that once the binary string 0 1 is shared, now then any set of this, any subset of 3 parties among these 4 parties, if they are curious and try to find out what is the underlying secret that dealer has shared based on what shares they have received, they will fail completely. That is what we have to ensure, right. So, imagine that in the first step the dealer picks the share S1 as the string 1 0, the share S2 as the string 0 0 and the share S3 as the string 0 1. Well, remember, it could be the case that S1 takes any possible binary string of length 2. Any binary string of length 2 can be a candidate S1 because S1 is picked uniformly at random. In the same way, S2 can take S2 can take the value as any binary string of length 2 and S3 can take the value any binary string of length 2 because all of them are picked uniformly at random. Now, based on the value of S1, S2 and S3, the S4 will be 1 0, the binary string, because now if you see that if you perform the XOR of 1 0 with 0 0 with 0 1 with 1 0, you will get the value 0 1, which is your secret S, right. But it is not the case that these are the only possible values of S1, S2, S3, S4 for the secret S equal to 0 1. It could be other possible vectors of S1, S2, S3, S4 as well, which could be the potential shares for the secret S if the dealer runs the sharing algorithm again for secret sharing the secret 0 1, right. So, now let us try to understand the privacy property, whether the secret sharing scheme satisfies the privacy requirement or not. And imagine that I consider the unauthorized subset consisting of parties 1, 2 and 3, right, 1, 2 and 3. Can we say that based on the values of S1, S2, S3, they learn anything about the underlying secret S? Can they say that okay, the secret S is 0 0 or 0 1 or 1 0 or 1 1 based on the values of S1, S2, S3? And the answer is no, because if you see the steps of the algorithm S1, S2, S3, they have absolutely no relationship with the secret S. They are picked independently of what is the value of the secret S. The S could be 0 0, S could be 0 1, S could be 1 0, S could be 1 1. S1, S2, S3 have got absolutely nothing to do with the value of the secret, and that is why you can say that the random variable GB, and remember from the earlier lecture, GB denotes the random variable, the GB is the random variable denoting the value of the shares S1, S2, S3, because I am taking B to be P1, P2, P3. And GB of 0 0 means the value of the shares S1, S2, S3 if 0 0 would have been shared by the dealer. GB of 0 1 means the value of the shares S1, S2, S3 if 0 1 is the secret. GB of 1 0 means the value of S1, S2, S3 if 1 0 is the shared secret, and GB of 1 1 means the value of the shares S1, S2, S3 if 1 1 is the secret. And this variables GB, it is a random variable, it is not a variable which always takes a fixed value. That is why we are now going to talk about the probability distribution. Remember, GB 0 0 within parenthesis means the probability that S1, S2, S3 takes different values with different probability given that 0 0 is the secret which is shared, and so on. Similarly, you can interpret the remaining variables. Okay. Right. So, since we have fixed my B to be P 1, P 2, P 3, in this specific case the shares that B 1, B 2, B 3 have learnt are 1 0 0 0 0 0 1. So, suppose these 3 people, right, they call each other and then they say to each other, okay, these is the shares that we have, these are the shares that we have received from the dealer, and now they are trying to learn the dealer's secret. We have to ensure that actually we have to show that they will fail to do that. So, by calling each other or whatever mechanism, if they come and meet and then they tell each other that okay, this is the share that they have received individually from the dealer, they will come to the fact that the shares that dealer has given to them is 10 00 01 respectively. And now they are making an hypothesis in their mind, they are trying to compute that what could be the probability that dealer has actually shared the secret 00 and the shares learnt by them are these shares, or what is the probability that dealer has shared the secret 01 and they have seen these shares and so on. So, from the viewpoint of the parties in B, the secret which dealer could have shared can take 4 candidate values, right, because remember the value of L is publicly known, the description of the secret space is publicly known. So, these 3 parties P 1, P 2, P 3 know that the candidate S could be 00 01 10 or 11. Okay. Now, it could be the case that dealer has actually shared the secret 00 and S 1 is 10, S 2 is 00, S 3 is 01 and S 4 is 11, right. It is quite possible, because if indeed you take the XOR of 10 00 01 and 11, you get the secret to be 00, but the parties in B do not know the value of S 4, because S 4 is right now not in this collection B. Okay. Only when S 4, if of course S 4 come with them, then together they are authorized, they constitute an authorized set. We are right now analyzing the case when an unauthorized collection of parties are trying to learn the secret. So, if the parties in B make an hypothesis that the dealer has shared the secret S being 00, that is quite possible, because it could be the case that the value of S 4 is 11. On the other hand, if the parties in B make the hypothesis that the candidate S, the secret S which the dealer has shared is 01, that is again quite possible, because if the missing S 4 is 10 and if S 1 is 10, S 2 is 00, S 3 is 01, then indeed the secret that dealer has shared is 01. In the same way, if the parties in B make the hypothesis that okay, the shares that they have seen correspond to the secret S, that is quite possible, because it could be the case that the missing S 4 which the parties in P 1, P 2, P 3 do not have is 01. And in the same way, if the parties in B make the hypothesis that dealer has shared the secret 11, that is quite possible, because it could be the case that the missing S 4 is 00. So, what we have argued here is the following: based on the values of S 1, S 2, S 3 that the parties in B learned, they cannot pinpoint whether the dealer has actually executed the sharing algorithm as per the first configuration here, or the second configuration, or the third configuration, or the fourth configuration, because each of these 4 configurations are equiprobable with same probability, and that is why learning the shares 1000001 does not allow or help the parties in B to learn anything about the underlying secret S. Okay. Now, assume that the dealer, the same dealer again runs the secret sharing algorithm, and assume that this time also his value of secret remains the same. Of course, the parties P1, P2, P3, P4 are not aware of this fact. It is only the dealer who again wants to share the same secret. And now, suppose during the first step, when the dealer is picking the shares S1, S2, S3 randomly, the values S1, S2, S3 takes these values. The shares S1, S2, S3 takes these values 1 1 0 0 1 1. It could be possible, right. If that is the case, then the share S4 will be 0 1. And now you can see earlier my S1 was something else, it was 1 0, but now my S1 is 1 1. Earlier my S2 was 0 0 for the same secret, now my S2 is 0 0, fine. Earlier my S3 was 0 1, now my S3 is 1 1, and based on what were the earlier values of S1, S2, S3, my S4 was 1 0, but now my S4 is 0 1. But my secret is the same secret, that means for the same secret 0 1, the vector of 4 shares could take different values with different probabilities. So, now imagine that a same unauthorized subset of parties P1, P2, P3 come together, and again they call each other and say, okay, this time we got the shares 1 1 0 0 1 1 from the dealer. Can they say anything whether the candidate S which dealer has shared is 0 0 0 1 1 0 1 1 based on their shares, and again the candidate S for them this time also could be 0 0 0 1 1 0 or 1 1, right. And it turns out that each of this candidate configuration could be possible for them. They cannot pinpoint whether dealer has actually run the secret sharing algorithm with candidate S being 0 0 or candidate S being 0 1 or S being 1 0 or S being 1 1, because for each candidate S that these people in B think in their mind, there is a corresponding unique S4 which is missing for them, and hence it is equiprobable that the shares 1 1 0 0 1 1 could be the shares for the secret S being 0 0, or could be the shares for the secret S being 0 1, or they could be the shares corresponding to the secret S being 1 0, or they could be the shares corresponding to the secret being 1 1 with equal probability, which shows that the random variable GB with respect to B being P1, P2, P3 is uniformly distributed. It is independent of whether the secret is 0 0 0 1 1 0 or 1 1, right. So, that is an analogy, that is an analysis when P1, P2, P3 are corrupt. Now, you might argue that what if my unauthorized subset consists of party P4, because as per the sharing algorithm the fourth share or the last share has actually something to do with the secret S. If the first n minus 1 shareholders are corrupt in the sense they constitute an unauthorized subset, of course, that does not learn anything about the underlying secret, because the probability distribution of their shares is completely independent of the secret. But what if in the unauthorized collection nth party is present, because the share of the nth party is actually depending on your secret S as per the formula that we have here in the sharing algorithm. It turns out that if I consider an unauthorized subset consisting of n minus 1 parties, say for instance party number 1 2 4, then if I take party 2, it has the share S2, if I take the party S4, it has the share S4, if I take the party P1, it has the share S1, and it is known that S4 is basically the unknown X. So, let me put the unknown S in question this box, that means its value is not yet known, XOR S1, XOR S2, XOR an unknown S3 which is not yet known, XOR S4, right. So, what are the things which are known to this unauthorized subset? So, they know S 1, they know S 2, they know S 4. So, if they substitute sorry not S 3. So, if they substitute the value of S 4, S 1 and S 2, they come to learn the value of S XORed with S 3. Now, does this reveal anything about the secret S? Absolutely no, because the missing piece S 3 here is picked independently at random, right, uniformly at random by the dealer, independent of the shares S 1, S 2, S of n minus 1, and hence it could be any S 3 XORed with any S which actually the unauthorized parties in B would have learnt. So, again let us make it more concrete. Let us take the example where say L equal to 2, the secret shared being 0 1, and these are the shares, and I am now taking an unauthorized collection consisting of 1, 2 and 4. So, party number 1, party number 2 and party number 4, these are the shares. For them the candidate S could be these 4 values, and again it turns out that for every candidate S that they think in their mind that dealer has and with which dealer has run the sharing algorithm, there is a corresponding missing S 3 which the parties in B do not learn, and since S 3 is picked uniformly at random, it could be the case that any of these 4 executions has happened and the parties in 1, 2 and 4 have seen the shares 1 0, 0 0, 1 0. In the same way, again if the dealer reruns his sharing algorithm with the same secret, then depending upon the values of S 1, S 2, S 3 here, S 4 could take this value, and now let us take the view of the same parties in B. Okay, this time their shares are now different, but again they cannot pinpoint whether this time they have actually seen the shares corresponding to dealer's secret being 0 0 0 1 1 0 1 1, because again this time also it could be any of these 4 configurations. Okay. Now, let us take another candidate group and see the working of the additive secret sharing. Now, this time my group is the group ZM, and remember ZM consists of the integers 0 to m minus 1, and this is my addition modulo m operation. The secret should be a member of ZM. To share a secret, dealer will randomly pick the first 3 shares as random elements from the set ZM, and now the 4th element or the 4th share should be such that the summation of S 1 plus S 2 plus S 3 plus S 4 modulo m should give me the secret S. That is how the 4th piece should be computed. And now once computed, dealer will distribute the shares like this. So, again let us take an example and try to analyze whether the privacy property is achieved. Imagine that the parties agree upon the modulus being m equal to 4. Remember the value of the modulus, underlying group operations, all these details are publicly known, and say the dealer's secret is S equal to 3. It has to pick the first 3 shares uniformly at random. Suppose it picks the shares 1, 1 and 3. So, now you see the first share and the second share turns out to be same. It is quite possible because they are picked uniformly at random and independent of each other. Now, based on the first 3 shares, the last share turns out to be 2, because if indeed you add 2, 1, 1 and 3 and then take modulo 4, you get back the result to be 3, which is your secret S equal to 3. So, now let us consider an unauthorized subset 1, 2 and 3. Again the shares S 1, S 2, S 3, it has got nothing to do with the secret S, and hence the probability distribution of the shares that the parties 1, 2 and 3 see during the execution of the protocol should be independent of the actual secret, right. So, in this specific case, what are the shares they are saying? So, this is one candidate value of GB, right. The shares S1, S2, S3 could take the values 1, 1 and 3, and these shares could be the shares for the secret 0 if the fourth share would have been 3. The same 3 shares could be the shares for the secret 1 if the fourth share would have been 0. The same 3 shares could be the shares for the secret 2 if the fourth share would have been 1, and the same 3 shares could be the shares for the secret 3 if the share would have been, if the fourth share would have been 2, right. But since the fourth share could be any of these 4 values with equal probability, hence it could be any of these configurations that actually the parties in B have participated. Again, let us assume that dealer reruns the same reruns the sharing algorithm, but his secret remains the same, and now this time it results in a different vector of shares, because now the values of S1, S2 and S3 all of them turn out to be the same. Again, the parties will not be knowing this, it is only the dealer who is running this, and based on the values of his first 3 shares, the fourth share turns out to be 2. Now, what will be GB, right. So, the GB will be basically the shares corresponding to the parties in 1, 2, 3 this time, and this time their shares are 3, 3, 3. Now, can it be the case that these 3 shares are actually for the secret being 0? Yes, provided the fourth piece would have been 3. Can these shares 3, 3, 3 could be the shares for the secret 1? Yes, provided the share S4 is 0 and so on. So, again this time all candidate S are possible from the viewpoint of the parties in B, and hence the parties in B does not learn anything. Now, what if fourth party is one of the parties in the unauthorized collection? So, let us take this unauthorized collection where the first party is missing, but the last 3 parties they call each other and then learn that okay, their shares are 1, 1 and 2. So, again similar to the case of where our group was consisting of strings of length L bits, if the parties in 2, 3 and 4 combine their shares, combine in the sense they make their shares, the value of their shares available to each other, they will learn something about the secret, but that something about the secret is basically the difference of S and S1, where S1 is picked independently of the secret S. So, since it could be any S1, right, which the dealer would have picked, learning S minus S1, the value of concrete value of S minus S1 does not help the parties in B to learn anything about the secret S, because it could be any S and any S1 whose difference would have been the value which the parties in B would have learnt. So, let us see this concretely. So, again the parties 2 and 3 and 4 in this specific case, they will be having access to these 3 shares, and they are arguing in their mind together whether they have actually seen the shares corresponding to secret being 0, secret being 1, secret being 2, secret being 3. Well, again it could be the case that dealer has shared the secret 0 because the first share was at 2, which together would have resulted in this shares. Or it could be the case that the share secret was 1, the first piece was 2 and then it resulted in this same shares 1, 3, 2. Or it could be the case that the secret was 2 and the first share was 0 and it resulted in the remaining 3 shares to be 1, 3, 2, and it could be the case that the secret was 3 and the first share was 1 and then the last 3 shares turned out to be 1, 3, 2. That means, for each candidate S there is a corresponding S1, and hence learning S minus S1 does not allow the parties in B to infer anything about the secret S. They are as confused as they were earlier. Now, imagine that the dealer runs the sharing algorithm again with the same secret, but this time the share vectors share vector is something else. Now, this time the view of the parties in B will be 2 to 1, because this time the shares that they are learning is this. Now, again you can see that it could be the case that dealer has shared the secret 0 with equal probability, it could be the case that the dealer has shared the secret 1 with equal probability, it could be the case that dealer has shared the secret 2, or with equal probability it could be the case that dealer has shared the secret 3. So, just based on these 3 shares, the parties in B cannot figure out anything. So, in this all these examples I am just considering one candidate B, right. You can take other candidate B's, run the sharing algorithm and then argue by computing these probabilities or just by mapping the candidate S with the candidate missing piece, and then you can easily find out that indeed it is the case that any subset of n minus 1 shareholders does not learn anything about any underlying secret, right. So, this is the summary of your n minus 1 out of n secret sharing, a very simple additive secret sharing. Here what is the share size of each party? Each party as a share is receiving an element of the group and the secret is also an element of the group. That means, whatever is the size of the underlying secret, the same is the size of each share as well, and it turns out that is the best we can hope for. We cannot design a secret sharing scheme where the size of a share is actually less than the size of the secret. That is the best. That means, the best we can hope for is that their share size, the share size is same as the secret size, and indeed this secret sharing scheme ensures that the size of each party, each shareholder is same as the size of the underlying secret, and hence this is optimal in terms of the share size. Now, an interesting question is the following: how do we instantiate a threshold T out of n secret sharing for any given T less than n? What do I mean by that? This additive secret sharing is a special case of threshold secret sharing, where your threshold T was specifically n minus 1. We designed the scheme in such a way that any subset of n minus 1 or less number of shareholders, if they come together, they fail to learn anything about the underlying secret. But what if my T is equal to say n minus 2, or what is my say T is equal to just 2? I want a scheme where any subset of 3 or more shareholders should be able to compute the secret, but any subset of 2 or less number of shareholders should fail to compute the secret. I cannot run this additive secret sharing for that case. I have to do something else. So, that means this additive secret sharing scheme is tailor made only for the case where T was exactly n minus 1, but in general I might be interested to design a secret sharing scheme, threshold secret sharing scheme for any given threshold T which is strictly less than n. So, that will be the focus of our next lecture. Thank you.